why do we want to use massively parallel processors? It turns out that in the past, 5 years, 4 or 5 years or so, there has been a very quiet revolution with some essentially the equivalent of electrical potential buildup, in industry. What happened was because of the power, constraints and also what we call the process variation issues. Intel, AMD, and IBM all had difficulties scaling their clock frequency up the way they used to. And it used to be a combination of microarchitecture techniques, which many of you know that I'm I built part of my career working on microarchitecture issues, and the process circuit techniques. And a lot of these things start to have problems in 2002 or so. So ever since 2002, the increase of clock frequency due to the combination of all these things and the instruction issue rate and all that for microprocessors slowed down. So this is the graph showing that the improvement of speed for just the raw gigaflops. That's essentially the clock frequency times the number of floating point operations that these processors can do, and the raw performance potential of these processors have increased very, very slowly for the past 4 years. Whereas if you look at processors such as the graphics processors from NVIDIA and from ATI, the competitor, they have a very similar curve going up. And it turns out that at this point, there is about 100 times of difference in the raw computational speed. Okay, I'm not talking about achievable ones yet. Okay, I'm talking about the raw speed that one can see from these chips. And so, for example, the calculation, is 367 gigaflops versus 32 gigaflops. And the 367 gigaflops is the version that you guys are going to use. It turns out that NVIDIA just announced a new chip, which is 518 gigaflops. So, that's about 7 months after this one, right? Okay, so, we're talking about a situation where you have a very big electrical potential buildup, and at some point, something is going to happen, right? So we're beginning to see that, that situation. There's another important thing, which is the memory bandwidth. The graphics chips have been operating right around 80 gigabytes per second into the main DRAM, okay, because of the frame buffer requirements and because of the relaxed memory model. And since I promised not to rely on 411, I'm not going to go into the very details about the coherence models and memory models, but just trust me that there are a bunch of things that general purpose processors have to support that make the memory bandwidth a lot more difficult. And with a simpler memory model, the GPUs have been able to get about 80 gigabytes per second into the memory. And there are 6 memory channels effectively, just pumping through the data. And the most recent chip supports over 100 gigabytes per second. Okay. So, Intel would probably go to the next SPI. That will probably go to about 20 gigabytes per second in about 3 years. So, that's kind of the situation. Until last year, what has been very difficult for anyone to use these graphics chips is that you have to use the equivalent of graphics API, meaning OpenGL or DirectX, Direct3D kind of things, and to program these chips. Even if someone builds a higher level programming environment, underneath it, they still generate code into the APIs. So the fundamental limitations of these APIs limit the kind of applications that you can actually write and you actually tune on these chips. That's why there were very, very few people, only with very heroic efforts, that can use these chips to get performance. And there are a few papers about it, but it's definitely not a widespread programming, phenomenon. All that stuff changed in 2007 because of the release of CUDA here. And NVIDIA actually spent some silicon area. Okay, so we're not talking about just software changes. We're talking about in the hardware, there is additional hardware added to the chip. So that if you use these G80 and follow-up chips for computing, your programming interface does not go through the graphics interface at all. There is a new general purpose interface on the silicon to enable this kind of stuff. And then all the software, other software layers were redone in such a way that you can do essentially C programming. Okay? And that really made a huge difference. And one very, very important thing that I'm going to kind of repeat a few times during the semester is that there is a big difference between what we call the elite systems and the sort of the mass production systems. Up until pretty much last year, when you learn parallel programming, when you do develop parallel software, usually these things are run on servers, on data centers, on departmental clusters. But the usage of these applications tend to be limited in that sense. Let me give you one example. If you want to develop, something like a, I would say, medical imaging application, it's fine to publish a piece of paper based on, let's say, a 64 cluster, a node cluster machine. But if you go out and look at the clinical usage of these, let's say MRI machines, all those machines are actually using the combination of a PC and some special hardware, accelerators. The reason is GE and Siemens would not sell their MRI with a big, racks and racks of, departmental clusters into the clinical setting. So NIH, for a long time, refused to fund a lot of these parallel programming, projects because they feel that the impact of these parallel software will be very limited because those huge cluster-based machines will not be in the clinical setting in the foreseeable future. However, with this chip, and with many, many other chips that will come out in the future, these things are going into PCs. For example, the particular chip that you're using this semester is the first massively parallel chip that will essentially go into all the PCs. The board, including that chip, is selling for $550. And most of you will have that for the games anyway. I'm not saying you're playing games, okay? None of you play games. But you will have a board in the PC just in case. So your friends will come over. So these GPUs or the equivalent of these things will be in PCs in the future. And whatever software that you produce will be used by millions and millions of people. The G80 series just passed 5 million units this month in sales, right? And I have not seen any 100 processor machines sold for 5 million copies in the past. Let me know if you know of any in the past. Okay, any large-scale parallel machines that sold for more than 5 million copies, right? Anyone? Okay, the largest one that I know of sold for about 2,000. Okay, so that makes parallel programming incredibly useful from real production use point of view. Now, what is this chip? This chip essentially is organized into what we call 16 highly threaded SAMs, streaming multiprocessors. So each half of this is a streaming multiprocessor. And for those of you who don't have computer architecture courses, don't panic yet. Okay, yeah, you know what, we're going to take you through in a fairly careful way. And if you count, each of them has a floating point add, multiply, and add unit in there. If you count patiently, there are 128 of those. Okay? Or you could trust me. Altogether, all these things run at 1.35 gigahertz. Okay? And so if you do the math, you will get something a little less than 367 gigaflops. What I haven't told you is there are special function units that also perform floating point units that can run in parallel, and that added up that difference. Okay? Each board comes with 768 megabytes of DRAM. And these DRAMs are different from the PC DRAMs. These DRAMs are essentially the frame buffer equivalent DRAMs. For graphical applications, these things hold the high definition, frames and so on. But for computing, these things appear like very high bandwidth, very high bandwidth, but somewhat low latency, regular memory. Okay, and you're going to be using these things, and I'm going to go back and show you how these things are used. The processor has 86.4 gigabytes per second memory bandwidth, and it also has 4 gigabytes of memory bandwidth each way. Okay, you can download from CPU at 4 gigabytes per second. You can upload to the CPU at 4 gigabytes per second. So altogether, it's a combined 8 gigabytes. But for any practical purposes, you'll probably be doing one way or the other. So it's about 4 gigabytes per second. It's PCI Express. Okay, and we're going to go through some of that later in the semester. So some important characteristics, okay? The peak performance is probably about 25 to 50 times of the current highest end microprocessors. And one of the people who are heavily involved in last semester's class, John Stone, who was here every lecture, and he actually gave one of the lectures. He actually ported one of his ion placement application, force calculation application onto this machine, and he got 265 gigaflops sustained for his application. Okay, very impressive stuff. And his paper just got accepted for publication, so we have not used his code as a benchmark and present results because we wanted to make sure that he could get published the stuff first. But we will be adding his stuff into the benchmark suite and so on. Massively parallel 128 cores, about 90 watts for that chip. And massively threaded sustains about thousands of threads per application. A good application will have about between 5,000 and 12,000 threads at the same time on this chip. Okay? And for those of you who are used to simultaneous multi-threading, Intel supports 2 or 4 threads depending on the machine model, right, per core, right? And this thing supports up to 768 threads per core, and 128 of them altogether add up to about 12,000 threads on this chip, okay? And it's very important to understand this particular view so that you can write effective programs. And we'll come back to this many, many, many times. About 30 to 100 times speed up over high-end microprocessors on science and media applications. If you spend an afternoon working on an application, you typically, if the application has what we call data parallelism, you can typically get about 10 times speed up, just spending an afternoon working on it. And then the rest, you need this course, okay? So, there's some comments. John Stone, made this comment. I think they're right on the money, but the huge performance differential. Currently, 3 GPUs equal to 300 SGI Altix Titanium 2 cluster will invite close scrutiny. So I have to, careful what I say publicly until I triple check these numbers. That was the reaction of many of the application developers last semester. They look at some of these numbers and said, this cannot be right. There's one extra zero. Okay? But, it's really good after you verify that stuff. And for you need to scrutinize your results. Okay? You need to check too. What's interesting about what we're teaching here? We have tons and tons of applications today. Okay, but what I think the world is going to differ in the future is that these future applications or future enhancement of the applications will likely reflect the world more than our current applications. Okay, so what do I mean here? If you look at the exciting applications in the future, a lot of these things are what we traditionally considered supercomputing applications. In the sort of biology world, we're moving more and more into molecular level. And Klaus Schalten is working on something called computational telescope. The idea is very simple. If you look at telescoping, it's something that we used to use optical or electronic means of essentially instrumenting a little system, right? And there are limitations of what we can do with these instruments. We can greatly improve these instruments by having a model that we simulate the underlying system and use whatever we instrumented as the initial conditions, as the boundary conditions, to enable some simulation. And then we can actually measure from the simulation even more details and more principles and more hypothesis verification than we can ever imagine to do with just a direct instrumentation. And that is an enhancement of a current application that can have tremendous implications. That involves a simulation of a very concurrent event, which is the molecular interactions of atoms and all these things. I pretend that I understand these things, right? So video and audio coding and manipulation. How many of you feel that you got to watch high definition TV to even get any satisfaction of TVs? And look at all the processing that you need in order to get high definition TV to work. And it's truly a very parallel process. 3D imaging and visualization. One of the things that we're going to see is that we're going to have much better user interfaces. If you look at Apple's iPhone interface compared to mine, let me confess, I still use this, right? So I just came back from Hot Chip, and at dinner we all put our cell phones on the table, right? And then so there were 3 iPhones, and I just kind of kept it in my pocket. So if you look at the interface and so on, these things, even iPhone still has a limited window, right? And if you think about it, the future direction of these things will be higher definition, 3-dimensional, perspectives and so on, so that you can really magnify that limited display, right? We're just at the beginning of these things. And, consumer game physics. Sanjay will be able to, in fact, I'll most likely get Sanjay to come and give a talk on the game physics. He just spent 2 years at AGEA and, working on a game physics chip, which is very similar to what, in many ways similar to what, NVIDIA chip is. And he will be telling you that when you drive a car in the games today, you're dealing with a pre-arranged sort of scenes, a set of scenes. And whenever you bump into something, it really doesn't change the future course of your driving, and it really doesn't change anything. It changes the score somewhere, okay, and then it reduces your life a little bit. But your wheels doesn't get distorted, and it doesn't make it any difficult for you to drive when you bump your wheel, when you lose one of your wheels, whatever, right? But in the future, these things will, because they are going to be based on physics simulation, and the wheels will bend, and they will continue to bend, and these things will make a huge difference in terms of experience, right? So these are all applications that actually simulate a concurrent world in some way, at some level. And there's tremendous amount of data parallelism, meaning you have a huge amount of data, and a lot of the computation can be done on different parts of the data in parallel, but you will need to reconcile at some point. Okay? So what goes around will come around, right? So there are techniques for doing that, and many of you here are from these application groups who actually deal with that on a daily basis. So the various granularities of parallelism exist, but the programming model must not hinder the parallel implementation. The data delivery needs to be carefully managed. And this is how you're going to learn here. Okay? One other important thing is this. For this particular paradigm, you're going to see these chips in pretty much all the new PCs that people are going to buy in the future. But not only that, NSF is building a whole generation of new supercomputers, what we call the track 1 and track 2 machines. The track 1 machines are at about 10 petaflops per level, and the track 2 machines are at about 1 petaflop peak performance level. And most of these machines will have the kind of things that I'm talking about here. And so when you do your research in the future, you will be able to apply these techniques that you learn in this course, not only to the PC level programming, but you can go all the way up to 10 petaflops. There will be one such machine here in Illinois in about 4 years. So for some of you who read these news, Illinois just won the NSF, petascale computing machine. It's a $208 million machine. And we cannot disclose all the details here because NSF is still finalizing the contract, especially. So, but in a couple of months, you will begin to see what I mean here. I'm not going to give you a whole lot of big picture, but I do need to give you this big picture before we go into the GPU focus part. So essentially, what happens is that traditional parallel architectures cover some of these super applications. DSP chips, there are plenty of these very high performance DSP chips that have been doing aperture radar, for example, those kind of things. GPUs, massively parallel graphics applications, network applications. Some of the Broadcom and Cisco, network routers are massively parallel chips. Okay, and scientific computing. So these things are what I call the peach skin methods. Okay, and let me explain why. If you think about the whole application space, all the applications that people have today, they roughly fall into 3 categories. The core is what I call the peach pit. Okay, what are those? If you go to Intel, they will tell you what they are. If you go to IBM, they will tell you what they are. The easiest ones of those got extracted and cleaned up into spec benchmarks. Okay, compilers, those are the easy ones. Then you have transaction processing, which tend also to be somewhat easy ones. And then you have a bunch of these customer applications that are incredibly huge, incredibly sequential, step-oriented kind of stuff. And they all fall into this pit. That is, whenever you try to apply your parallel computing technique into these applications, it's like biting into the peach pit. Okay, it's not a good feeling. Try it once. I actually did it. Last time when I gave this lecture, before I gave the lecture, I actually tried it, and there's a little chip right here. Okay, seriously. So I like to know what I'm talking about, right? So so this thing is very, very hard to parallelize. And when Intel and AMD and Microsoft work on some of these multi-core chips and many-core chips, they need to actually bring some of these people forward. Very, very hard business. Okay, and then we have what we call the peach skin applications. We have scientific applications. Some scientific applications that are fairly easy to parallelize. We have some of these early graphics applications, but they only account for a very small amount of what I call the exciting applications in the next 10 years. because they don't still cover some of the very exciting things. For example, if you look at medical imaging, most of the real applications are still being run on this kind of stuff. But they really have the opportunity to get to the performance level of this hundreds and hundreds of times. So what those applications are what I call the peach meats that are ready for someone to eat, enjoy, and so on. But neither of the hardware have been able to really take advantage of those things until something like CUDA came along. So NVIDIA is actually moving their previous generation graphics processor. Remember the GPU API interface and all that, right? So it makes it so hard to program that only a very small number of applications can run on that machine, and they're the skin. So with CUDA, they're trying to cut into more and more of the meat and support more and more of these more general applications and get more benefit. And Intel is actually trying to go out from here, use multi-core and extend some of these with more robust memory models and so on, try to capture some of the opportunities here. Eventually, they're going to meet up. Okay, I predict in 10 years the world will look, they will converge at some point. But what I would like to do when I teach this course is that if you have a 2-core system, it's hard to get more than 2 times speed up out of a 2-core system. And it's hard to get application developers to be excited about 2 times speed up with all this work that you're going to learn for a whole semester. Instead, what I do is I teach you how to use 100 cores and get some really exciting, things going on, and get some really exciting applications. Not all the applications will work, but we will be operating in this ring here, right? And as these architectures push towards each other, most of the techniques that you learn will eventually apply to all of these. Okay, and that's the vision. And I believe 10 years from now, you will think, you will say that he is right or he's totally wrong. But I like to take this kind of position. All right. So what are the previous projects? So previous students in this class work on video encoding, fluid dynamics, cracking, RCS 70-bit code, finite element modeling, quantum chemistry, right? Polynomial equation solver, network simulation, LINPACK, essentially linear algebra, astronomy, 2-point angular correlation, and finite difference time domain, for antenna design. And most of these things were actually sponsored. There is a MRI application at the bottom, MRIQ. And most of these things were actually sponsored and mentored by application groups. So, the source code varied dramatically from several hundred lines to tens of thousands of lines of code. So you can pick what you feel your software skill will be able to handle, right? It could be, so for some of you, it could be 1 million lines of code. In fact, I'd love to have one of you to work on a 1 million line application, okay? And that will be spectacular, right? And some of you will probably, focus on a few hundred lines of code. But, for example, this one, there's still some issues that we didn't really resolve. And then the kernel is actually what someone crafted in this course, and eventually some of my grad students cleaned up. So these are the typical lines of code that people ended up crafting into massively parallel things, right? And in some cases, for example, in this case, if they crafted another 400 lines, this number would have been a lot higher. I took some points off at the end of the semester because of that, right? How many times of speed up can you expect out of this application? Give me a very quick answer. If they did a perfect job on this one, would they get 2 times speed up for the entire application? This is the percentage of time spent in the part that they parallelize. The best they can do is to slash up 16% of the execution time, right? When you pick an application, you really need to figure out how many lines of code you will need to parallelize in order to get to something like 99%, in order for you to get real speed up. Remember, If you eliminated 99% of the execution time, you get 100 times speed up. Understand the concept, right? So if you are doing something less than 100, taking care of less than 99% of the execution time, you're not going to get more than 100 times speed up. Now you should have a lot more respect for people who got 300 times speed up and 400 times speed up, right? Okay, think about that. Okay, now we were getting things like 200 times speed up and 400 times speed up. In general, the 10 times speed up things typically are typical, and they saturate memory bandwidth. Typically saturate memory bandwidth. So you need to figure out how to get around the memory bandwidth limitation, which is the local memory utilization, which is some of the transformations that you need to do, and those come in the lectures. Okay, and then for the good ones, people were successful in getting around these things. They were 25 times to 400 times speed up, and then you will run into limitations such as register size problems, such as local memory capacity problems, such as time stepping problems in algorithms. So these are the things that you will raise yourself to the next level, and then learn more about how you can get to even thousands of times in the future. And keep in mind the speed up also reflects how suitable the CPU is, because in some applications CPUs are doing great, so it will be harder to speed up these things. So one thing that you also need to learn is to give the CPU a fair chance. You need to make sure that the code is actually written nicely for the CPU. It's not just to make yourself look good. You also need to honestly look at how you can actually improve the CPU performance when you do the comparison. So that's the introduction.